Yeah, so today we'll discuss about the address modes in ARM processors, the multiple register load and store commands, how we'll be using embed C and Keil, and how you can use it to do some implementations, and how to sort an array in assembly language using bubble sort. So let's get right into it. We'll start with the address mode. So we have three broad address modes. The first one being pre-index mode. The second one is pre-index mode with write back. Now, says that the only difference is the exclamation mark syntax file. You'll see what I mean, but just keep this in mind for now. Okay. And then you have post-index mode. So these are the three main index-wise classifications that you can do for the address modes of LDR and STR commands. Now, there are two more subtypes in each, which of which the first is immediate offset addressing, in which you use a predefined constant. You provide a constant to the instruction saying that I want this number as my offset. Okay. And then you have a relative offset where you provide the offset through a register. Okay. So a register will have the offset value that is going to be used in the instruction. So we'll look at each of these in detail. All right, let's first go to pre-index mode. Okay. Now in pre-index mode, syntax is the following. Like I said, immediate offset addressing uses a constant value each time for the offset, and relative offset addressing uses a register to give the offset for the instruction. Now, an important thing to note here is you can have the offset as 0. Now, if the offset is 0, you don't need to provide this parameter. Okay. So you can just put square brackets right after R1 and omit the rest of the command if you want a 0 offset. So now we'll look at what these commands do. So str is store register into memory, right? So it will store whichever register is here in the first argument into the memory location at R1 plus offset. So basically, whatever is given in the square bracket, it will store the value of R0 into that memory location. Okay. Then similarly for R0, R1, R2, it will store the register R0 into the memory location R1 plus R2. Okay. Now, an important thing to note here is that the value of R1 does not change. Okay. Even though you provided an offset over here, the value of R1 will not change with this command. So we'll just quickly look at this command in Keil and see what sort of output it gives us. All right. So here's the pre-index mode. All these programs are available on your OLP MBSD repository, so you can get it from there. All right. Okay, so let's just have a look at this. We're loading the register R0 with a value 1, 2, 3, 4, 5, 6, 7, 8. And then we're trying to store that at 2 followed by 7 zeros plus 4. Okay. So if we just run this, okay, you can see that at the bottom right of the Keil window, you have 2 followed by 7 zeros. So this first set of two numbers, two hex numbers, is your 0. Then this is 0, 1, 0, 2, 0, 3. And then starting from 0, 4, you can see that this number has been stored. Now, if you paid attention during little endian and big endian, you'll see that this number has been stored 1, 2, 3, 4, 5, 6, 7, 8 from right to left, right? So higher bits go to higher memory addresses. So that's your pre-index mode. Now you can see in the top left corner where the register values are given that the value of R1 has not been updated. Right? We started off at 2 followed by 7 zeros, and it's still at 2 followed by 7 zeros. Even though the value of the register R0 was written at 2004, right? So keep that in mind because it will be important. Right. So I have deliberately not done any animations on the next slide. Just look at this, okay? Look at this part, the right side closing bracket on both these commands. So the next command that we'll be seeing is pre-index mode with write back. Okay, so the only difference, as I had mentioned, syntax right, is an exclamation mark. So if you see this, the syntax is exactly the same, but there's just an exclamation mark at the end. Now, this is almost the same as the previous, but it just does one thing extra, which is the updation of the value of R1. So previously, you saw that the value of R1 was not being updated, but now you have R1 being updated to R1 plus offset or R1 being updated to R1 plus R2, depending on which type of command you're using. So if you use immediate offset addressing, it will update to R1 plus offset. If you use relative offset addressing, it will update to R1 plus R2. So yeah, note that the value of R1 is updated in this command. Pretty important. I'll just look at that in Keil. So here we have the pre-index mode with write back file. And you can see the only difference here, everything else is exactly the same. There's just an exclamation mark, right? So we'll just remove the semicolon. Build the file. Right. And now you see again, after I ran it, once again, it's at 004, right? It wrote it at 004. Okay. But this time, it also updated the value of R1 like we expected it to. That's why it's called pre-index mode with write back. So it's writing back the value of R1 plus 4 to R1. Okay, that's pretty intuitive way of remembering it. So that's pre-index mode with write back. Okay. Any questions so far? Okay, we'll continue then. The next one we'll be going to is post-index mode. Now, if you look at this, the only difference from pre-index mode is that the offset is written outside the bracket. Okay, so what does this do? Now, you covered accessing the memory location at R1 plus offset in both pre-index mode. But what if you want to update R1, but you don't want to access the memory location at R1 plus offset? You just want to access the memory location at R1. So this is what post-index mode does for you. You can access the memory location at R1 and then set R1 to R1 plus offset. So this is particularly useful if you want to access a range of values one by one, like in a loop. Let's say you're comparing adjacent values to each other. So each each time you access it at R1 and then change R1 to R1 plus offset. So R1 comma R2 will update it to R1 plus R2. And in this command, the value of R1 is updated, but you access the memory at location R1 plus offset, or R1, just R1, sorry, just R1. Okay, keep all these in mind because uh, when the teacher, when ma'am taught it to us, it got really confusing. So to make sure you guys are following along, otherwise it's quite easy to get lost in these topics. Okay, so we'll just look at post-index mode in Keil. Right. So this time, if you see the code, it accessed and wrote to the memory starting from 2 followed by 7 zeros itself. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. It wrote it directly at 0, 0. And after it wrote the memory values, it updated R1, as you can see in the top left corner, to 20004, right? So that's post index mode for you. Yeah. Now we'll just one small note. Someone might be confused as to why we're only covering STR commands and not LDR commands. It's quite simple. The LDR command just functions the exact same way, but instead of storing into the memory, it loads the value from the memory. So you have the syntax right here. It's just literally replaced STR with LDR. Everything else is the same. All right. So here's pre-index mode. Then you have pre-index mode with write back, and you have post-index mode. So these are all the same, just that you replace STR with LDR. Okay. Now, another type of addressing that you can use in assembly language is using shift operators with the index mode. So you can use this only in relative addressing mode. Okay. So you know how you can provide a constant offset. It wouldn't really make sense to left shift that offset because you can just provide the left shifted value directly. But sometimes when you have a value in a register and you want to left shift that, so that's where we can use this. An important thing to note with this is that you can only use LSL, which is logical shift left. So you cannot use ASR and LSR. You cannot use ASR and LSR for this command. And here's the syntax. So pre-index will access the memory at R1 plus R2 left shifted by X. All right. R1 plus R2 left shifted by X. So only R2 will be left shifted by X. Okay. Now keep in mind that this is left shifting the binary value, not the hex value, because sometimes you may get confused and left shift 0x01 to 0x10, which is not really correct. Okay. So keep in mind that it shifts happen on the binary values, not on the hex values. Then you have pre-index with write back. This is the same syntax, just an exclamation mark added to the end, but R1 is updated. Okay. Then you have post index where the register is outside the square brackets and you write LSL. So it accesses the memory at R1, stores the value into R0, and then updates R1 to R1 plus R2 left shifted by X. Alright. Is all this clear? Does anyone have any questions of any sort?
No.
Okay, then we'll move on. So now we have multiple registers load and store command. Now the thing about this is, let's say you have a bunch of data in your memory and you want to load it in. Of course, you could do, write a load store instruction into a loop and then one by one load it into the registers that you need. Or you could write multiple move instructions and then load the values into the registers as you need. But of course, that's not efficient and very helpfully provides us with load store instructions for multiple registers. If you want to load multiple register values, you have for loading purposes the LDM command. Now here you have an optional modifier called address mode. So we'll look at this in a little bit. And then you have an exclamation mark here. So we'll look at that as well. And then you have for storing multiple registers, you have STM. Okay. So this is load multiple LDM and STM is store multiple STM. So the curly brackets, they specify optional modifiers. So it is not necessary to specify the address mode, but you can if your application requires it. All right. Now, usable modifiers. The address mode, uh, you have IA, which stands for increment after. So it loads or stores the register value at that address and then changes the value of RD. In this case, it increments the value of RD after retrieval. Okay. And in case of DB, as the name suggests, it decrements the value of DB of RD before accessing it. Okay. So then you have the exclamation mark where it updates the value of RD after each time. Now you might be wondering, if I have IA but no exclamation mark, how will that work? Because it's not updating the value of RD. So don't worry about that. We'll cover everything. And then you have reg list after that. So in reg list, you have to use curly brackets and provide a list of registers that you want to populate or a list of registers that you want to store into memory. All right. Now you can pass either a comma separated list such as R0, R2, R5, or you can, let's say you have 10 registers, so it would be really silly to write R0, R1, R2, R3 all the way up to R9. So you can just do R0 dash R9. So that will cover every single register in that range. Now, if you want to provide a mix of those two styles, that is also allowed. So if you want to do R1, R3, and R5 to R8, you can do that too. Okay. Now let's look at these commands in action. So we have, okay. Do you guys know about DCD and DCB? I think you know about some. I saw some people using DCB in the assignment,
Oh, wait,
but
that was only me.
yeah, yeah. Okay, I'll just explain DCB and those things in a bit. So let's say we have. Okay, so design DCB first off. DCB stands for define constant byte. Okay, and constant byte. So it's of these values that I've provided into hexadecimals of of 1 byte. So that would be, let's just see it. Okay, if we remove the, all right, now you see it says one error, right? So it says the first value that I've provided, immediate FEDC 1234 is out of range, should be below 0x100. Now just look at the calculator. 100 is basically 8 bits long, right? The ninth bit is 1, but it's saying it should be less than that. So what's one hexadecimal less than this? FF. So it's saying that the value that I've provided should be either FF or less than that. So 1 byte has 8 bits, so you can only store 8 bits worth of data in using DCB. So if you want to define a string, if you've seen the ASCII table, you can see that this only goes up till 127, right? So you don't really, and the hex goes up to 7F, which is less than the maximum that we had. Isn't that right? So we look at the calculator, you can see that FF goes up to 255. So if you want to store a string, you can use DCB. You can do something like string DCB and then provide the string here. Let's say hello 103, and you need to provide a 0. Now what this 0 is, if you've learned about null terminated strings in C, so basically assembly has the concept of null terminated strings. It uses, it identifies the end of the string with the null character. So you should, it's good practice to end a 0 at the end so that it turns into a null terminated string essentially. So each character will be stored as two hex values next to each other. All right, so that's how you define a string. But now we have a problem, right? Because we want to store a full 32-bit value into our memory, but we can't do that. Let's say we wanted to store a slightly larger value, but not 32-bit. So let's say we wanted to store a 16-bit value. So in this case, you see here it says word, right? So a 16-bit value is called a word. Now you can use DCW, which stands for define constant word, to store values of 4 hexadecimals, or let's just, I'll just, we hit F7. Yeah, so you can see the error has changed a bit, where it says it should be less than 0x1 followed by 4 zeros this time. So if we just check this out, 1 followed by 4, So you can see that. Okay, it's in Q. So one followed by would,
Abhishek,
yeah.
your voice is getting muffled in between.
Uh, is it okay now?
Yeah, yeah, it's better.
Yep.
Okay. So if you have one followed by four zeros, then you can see you have 16 bits of zeros over here. So it's saying this DCW, defined constant word that you are doing, needs to be less than this value. So what's less than this? You have, oh man, yeah. So one less than that is all is four Fs, which will be 65535. So if you've done, I'm not sure if C++ or C have these data types, but in Java, you know that there's byte, short, int. So we had byte. Now word is basically equivalent to a short, where it goes up to 65535. And then what if you wanted to use the full 32-bit, capability of your ARM processor? Like, I want to store big numbers, why can't I? Right. So in that case, what you use is DCD, which stands for define constant data. Okay. So now if you see, if we translate this, it's changed to one warning, which if we build again, it will disappear. So we've defined the array. Just remember that you can define strings with DCB. You can define smaller integers with DCW, which is defined constant word, and you can define full 32-bit data with defined constant data or DCD. Okay. Then let's just look at this. So this command stores the value of this array, sorry, the address of this array into the memory. Now here you'll notice that we've added an extra line in over here, right? So what this is because if you'll notice here, we're in the area code read only. Okay, so this area is read only and you can't really write to it. I mean, in this case, we're not writing to that area, but let's say further down the line, we want to modify part of this array. Then we'll have to define this in the read write zone. So we've just changed the area that we're working with to read write. Okay, we've called it data, and then we've defined it. So if you've paid attention in class, then the teacher would have told you, or the slides mention that the first writable data address that you have starts at 2 followed by, okay, that's 1 0 less. So it starts at 2 followed by 7 zeros. That's why in all of these examples, I was using this address, all right, because this is the first user writable address. Everything before that contains space for code and instructions data and things like that. So you can't really write there. You can read from it, but you can't write to it. So if you wanted to define some variable over there, you could, but you cannot change that defined variable. Okay, keep that in mind. So this will,
Is it like the the final function in Java, is it similar to that?
I guess you could say that in a sense. Yes.
Okay. Okay.
So yeah, this command loads the location at which the first element is stored. So this will be, I'm not sure if that's the right number of zeros, but you get the idea. Then I hope you're aware of this. If you want to move a register with the full 32 bits, then you cannot just do it in a single move instruction. You have to first do move W and move in the lower 4 hexes, I mean the lower 16 bits, and then you have to do move T and load the upper 16 bits. So that's what I've done here. So this is 20028, and I've chosen that value because after every 4 increases, if you see, you have 1, 2, 3, 4, I think the 10 data values here. So after every 4 increases, multiply that by 10. You don't get 40 in hexes, you'll get 28. Okay. Hex 28 is decimal 40. Okay. So when we're loading it back into our registers, we'll use 200028 to load those values from the memory into our registers. Okay. So just run this program. Right. So R1, R11, sorry. R11 has, as I said, 2000. R0 and R1 have some internal values that you can ignore. You have the loading in R12. Now, once you execute LDM IA, okay, so this is load, multiple, and increment after, right? You see that this entire memory starting from 200, the part that has been highlighted green, all right, the part that has been highlighted green, that is what was red right now. Okay, so we started from 200 and we went all the way up to 28. As you can see in this memory address, it incremented after. So now it's at 28. Now we want to store those somewhere else. So we're storing them starting from 28. All right, so 28 is blank, and just above that, 28 is where we're starting the blank space. And just above that, you have all these values that we just defined in our array. So you can see they've been loaded into the registers properly. Now, the next is STMIA. So this is store multiple, increase increment after, starting at the address mentioned in R12, and it will update the value of R12 because of the exclamation mark. Since I've defined R0 to R9, it will write all of these values starting just after the 38. Okay, so let's step. Okay, now you see here it went into the crash handler, but ignore that. So this is the 20028. So you can see that it basically copied all of these values starting from here all the way up till here. And if you look at R12, it is now 50. ending in 50. So that's basically the LDM IA and STM IA commands. Now, we talked about just IA with the register updation. Now, what will happen if I remove the exclamation mark but still keep the IA? What do you guys think? Any guesses?
Uh, the value will go back to the original after the thing is done.
They are saying that everything will just be written to R11's point, and uh, basically everything will be overwritten again and again. Is that what you're saying?
No, that's not what would
No.
happen.
Then
Everything will be written the same way, but like R11 would stay the same at the end of the program.
okay, let's take a look at what
Like the
happens.
value of R11 wouldn't change, like it
Alright,
was before at every step.
right. They're absolutely correct about that. Uh, it didn't even update. Second. Right. So R11, as you did say, was not updated, but it stored it in the exact same way. Okay. Now, similarly, you can try this with STMDB and remove the exclamation mark there. So it will do similar things. So if you don't add an exclamation mark, it just won't update the register, but it will function the same way. Okay. So you can try out the various modes in Keil. Like just take this file from the repository and then you can modify it, change it a little bit, remove the IA, keep the exclamation, things like that. Okay, just try it out, experiment a little bit, and then you'll find out in depth all the things that will happen because we're kind of running out of time. So let's not go into too much depth. You guys can try it out on your own. Okay, but just keep in mind that removing the exclamation mark just makes it so that the registers don't update, but the command functions as it normally would. Okay, so that was multiple register loading and storing. Now, from what we've learned till now, you can solve all of these questions that are given here. Now, these are also given on the repository, and I would recommend that you solve them so that you get a better understanding. I hope you guys know about loops. I did see some loops in the assignment previous one. So I'm guessing you do know about loops. So these are the assignment questions and they are available on the GitHub repository. So you can check them out there and have a quick read through. If there's anything you want to ask right now, you can ask. I'll give you like a minute or so.
Could you discuss lab 2 assignments?
Lab 2 assignment. Okay. Which
Yeah,
question in
question
particular?
2. Question 2.
So the counting of the string.
Yeah, counting of the letter in a string.
Okay, we'll discuss that. Okay. But before that, I'll just cover up the stuff that is left. That's fine.
Okay.
Okay. So another really important topic that we need to do is using embedded C in Keil. Okay. Now you might start wondering, array, already we have assembly to deal with. Keil is not that great of a compiler. Why are you introducing something like embedded C? Now the thing is, embedded C is really useful for higher level applications. Now you can imagine doing something like uh, you know sorting through an array, or if you've ever gone to any competitive coding programs, like gone through the questions, imagine implementing something like that in assembly language. It would be an absolute nightmare. Like just writing a single loop becomes complicated to follow. If you write nested loop, you'll just like you won't be able to debug your program if you're not getting the output that you want. And it's also really convenient for stuff like sensor value retrieval, motor control, when certain conditions are met. You'll see what I mean. Embedded C is fast. I mean, it's not as fast as pure assembly, but it's still much faster than languages like Python and Java. Because, and it's much more readable than assembly language. As I just mentioned, if, imagine debugging nested loops in assembly. It'd be an absolute nightmare. I mean, you could do the debugger stepping, but will still end up much less convenient than you could debug an embedded C program. So since it's called embedded C, you can make the assumption, like you can make the connection rather, that it's the bridge between the proper C programming language and assembly language. So it's designed for embedded systems like microcontrollers, and it's a higher level version of what you can use in a microcontroller. Now, for those of you who are into this kind of stuff, you can use embedded C on Arduino as well. So that can allow you to get some insanely fast speed if if your application is time critical. So look into that if you're interested. And it has nearly the same syntax as regular C programming. You know about pointers and how to use those, right? So the only difference in embedded C is you have something called as port registers. So our microcontroller, which is the MSP432, has you see this file, embedded C test. Okay. So you'll see first thing you do is you disable the watchdog timer. Now you know what? I won't go into the details of what this program does. It basically toggles the bit 0, which is basically the what do you call it? The port at which the LED, one of the LEDs of the board is connected to. So if you keep XORing the bit with 1, it will keep toggling, right? So 0 XOR 1 is 1 and 1 XOR 1 is 0. So you keep doing that. So the output of that will keep changing. And this is basically just an empty loop to provide a delay. Now, if you wanted to use a microcontroller, what you do is, oh, sorry, not this one. You go into options for target, and here where provided where you said that you want to use a simulator, you need to actually see these high level changes. This Keil does not have a port register monitor. I mean, as far as I know, it doesn't have a port register monitor. But to actually see these changes happening, you'll have to use a proper microcontroller. So you can change the option to this, and then when you go to the settings and you have a proper microcontroller connected, all these things will just get filled in on their own, and you can select something, right? You can select the device here, and it will automatically detect all these things for you. So for now, we'll just use the simulator. You won't be able to see any blinking LEDs or anything, but I'll just show you how it looks like. So we'll just exclude this, include this in our build. and debug it. Okay, now you look at the states register, alright. If I start running, okay, now you can see that it's running continuously. Every time I click on registers, you can see that all these values are updating. Okay, so just look at the states and the seconds value. You can see that the program is running in the background. Okay, so we don't unfortunately have a port register monitor over here, but you can see that the code is running. You can see the value of state updating every time I click the registers. So if you actually want to use this, if you want to use embedded C, you'll need a proper microcontroller connected to your system. Otherwise, you won't be able to visualize the changes. So that's embedded C. Now, what I'll do is, yeah, I'll cover. Okay, I have a suggestion. Like we'll cover bubble sort, and this program is quite complicated and it uses arrays and everything. So I would recommend you give that counting the occurrence of a character in a string another shot after I explain this bubble sort program. And then if you still have questions, come and ask me. Okay. Like you'll see why I'm saying this. It's not like I don't want to explain, but I feel that if you see this program, once I explain this program, it should become quite clear as to what you need to do with the string sorting, the string counting program as well. So that's all we had to do for embed C and Keil. Oh yeah, another thing that Ravikant sir told us to mention to you guys is that there's an updated version of Keil, and in that you don't have to add all these startup files into your source group. So I don't have the updated version, but when you do update, you don't have to add these in anymore. They'll just automatically get detected. That's a nice thing. And now the program that you dreaded is finally here, bubble sort. Now I'm here to demystify it for you. It's not that hard. Yeah, not that hard. We'll just go through it step by step, and there are comments explaining each and every line. So we'll go through it command by command, instruction by instruction. So if you ever feel like you're not understanding, just stop me. Okay. So we've got this huge array over here. Now, if you look at the programming calculator, I have now I have the number 79,046. Now, if you remember, the limit for 16-bit was 65535. So we can't store this within 16 bits. So we'll have to use the DCD command. All right. So we'll use DCD to store our array, and then we'll get into our code. All right. So here's our code. Okay. So now R0 has the address of our array. And you can see here, the first element is 7C, and then 00000007C. So that's our first element, which is micro. 7C is 124. Okay. Just keep this calculator appended over here. So let's step to the next one. We need to provide it with the size of the array. Now in my case, I have 8 elements. Right? So I've provided R1 with the size of the array. Now let's step to the next one. Now R2 holds the current element number and R6 holds the number of swaps. Now one important thing to visualize is think about the bubble sort algorithm. Okay, so you have adjacent elements being swapped if the first one is greater than the second one, right? So if you make one complete traversal of the array and there are no swaps, that means that the array already has everything in the perfect position, right? So that's why we're maintaining a count of how many swaps we have had. Okay, so it starts off at 0 and R2 is our current element number. So we'll have R2 as 0 as well because we'll start off with element 0. Okay, now let's step equal to 0. Now you store the next element number, which is R3 equals to R2 plus 1. Now you compare whether R3 is greater than R1. Now R1 is the size of your array, right? So if you have gone past the size of your array, that means you're outside and you're just comparing it with rubbish, right? So you have to make sure that you don't go outside. Now the next statement, once we compare, is branch if greater equal, right? So if we've reached the end, then we branch to B sort check, which will come to in a bit. Okay, so we've not reached the end, right? So into R4, we read the current element value. Now, what is the current element's value? You have 0 left shifted by 2 plus the value stored in R0, right? So R0 plus R2 left shifted by 2. Okay. So if we load this in, you'll see that we got the value, the first value that's been highlighted in green. Okay. So we got this value into our register R4. Now when we move on, you can see that R5 gets the value of the next number, which is 134C6. Get 134C6, 79,046, right? Which is the next number in our array. So that's been loaded into R5. Now obviously we're going to compare the two numbers. Now what does bubble sort do? If the two adjacent elements, if the first is greater than the second, then it will swap, right? But in this case, our first element is already smaller than the second. So we'll compare. And now just look at this command carefully. These two commands. Okay. Store if greater than. Okay. So if the result of compare was that current, which is R4, is greater than R5, then you store that value, the value of R5, into the memory location of R2. Okay, so so where we loaded in R4, we are now storing it in R5. So if it is greater, see, we are swapping the addresses of the two. Okay, so if it is greater, R5 is being stored at current element position and R4 is being stored at next element position. So in our case, it is not greater. So you can see that the memory is unaltered, right? So if we did swap, then you add 1 to the number of swaps. But since we did not swap, we'll move on. And now we move the value of R3 into R2. That way we can move to the next element and then we branch back to the beginning of the loop. Here again, we look at the next element number and we compare it with R1 to see if we've exceeded the size. If it's greater or equal, we branch. Since it's not, okay. Now we'll load these in. Okay. Now you can see that this time R4 is greater than R5. Okay. Just look here. You have 79,046 and you have 10,293. So obviously these should be swapped, right? So let's see CMP R4 and R5. Now keep an eye on this memory down here. Okay, when I'm executing these commands, just keep an eye on this memory. Okay, so once we step, you see that it wrote this value to this register, this memory location here. And when I execute the next command, it wrote the higher value to the right side. So it basically swapped the positions of the two elements. Okay. Now since we have swap, it will increase the value of R6 by 1. Okay. Then you move to the next element again. Guys, should I speed this up a little? Like, I mean, I've shown you one not swap and one swap, so I'll just, you know, if it's cool with you.
Yes, of course.
Okay. Then we move back to the beginning again. And just keep watching the memory. Okay, I'll just speed it up a little bit. Okay. So we've loaded in R4 and R5. Again, R4 is bigger. So watch the memory. It will get swapped again. It got swapped. Then since it got swapped, we'll add 1 to the swap counter. Next element. And all right. Now again, you see R5 is smaller. So what's the memory once again? It will get swapped. All right. You see it got swapped. Add 1 to the swap counter. Move to the next element. Keep going. Again, you see that it's smaller. Like you can see, this is the second biggest value in the array. So it will go all the way to the end. It will keep swapping. And just when it wants to compare the last two, which is 6A39, sorry, 01396A with this one, 13436, that the last iteration is where it will not swap, right? So we'll move ahead. So again, you can see in the memory here, swapped it, add to the swap counter, go back, check again, swap. Okay, now to the second last iteration. See, last iteration. See, now here you see R4 is smaller than R5. So this time, if you watch the memory, it will remain unaffected. After, we will not increment the swap counter anymore. Okay. Now we increment R3. Now you see we've reached the end and you can see that R3 is equal to R1. There is nothing in front of that. So if we go ahead, it will branch to B sort check. Now what this does is, as I mentioned in the beginning, if you traversed the array and found no swaps, that means that it was sorted, right? So we compare it with 0, and if it is greater, now do you remember in bubble sort, the inner loop, we always decrement the value that it goes to one by one. So like it starts off that we traverse it till the very end, and then we traverse it to end minus 1, then end minus 2, end minus 3. So bubble sort basically makes sure that in each iteration the heaviest element reaches the end, right? So if you look at our array here, the heaviest element 80234 made it to the end in the first iteration, right? It was our luck that the second heaviest element also made it to its right position. But basically, now we can reduce the size of the array that we need to check by 1. So that obviously, since the heaviest has reached the end, you don't need to check if that is greater anymore. So we'll just move ahead. And now R1 is 7. And it continues on sorting just like this. Okay. It keeps changing. I don't want to. See, there have been. Okay. There was one swap. Okay, so this is. Now we're at 5. Now we're at 4. No swap yet. Alright, alright. Oh, sorry. I sped past it. Uh, right. So you see, R6 is 0. So this basically means that the array that we have right now, see this 7C, oh sorry, 00007C, then you have 0 to 8F, then you have 0 to AA, which is bigger, then you have 2835, which is bigger, then you have 3815, then you have FB, F5, then you have 0134C6, which is bigger, and then you have the biggest 01396A. So you can see that this has worked and in fact did sort our array in place. So that's bubble sort, the whole program. Now I hope this clarified a bunch of stuff for you, like how to use the compare instruction properly, how to use LDR, how to use you know, conditional branching, conditional instructions. So I would like to give, I would like you guys to give let's character counting program another try now that you have uh, you know, understood this explanation. I mean, hold on, you guys have understood this explanation, right? Any questions about what?
Yeah, why do you left shift all the values by 2 bits?
All right, so you can see that all of these are 32-bit values, right?
Yeah.
So in this hex table that's showing memory location, you can see that this is 00 01, 02, and 03. Okay, and then the next value starts at 04. So you would want to add 4 every time you want to, you know, check get the next character. So you have 1, and then you left shift that by 2, you get 4. So each number of hours is occupying 4 spaces, right? So that's why we left shift our counter, uh, our memory location by 2. I hope
Uh,
that.
does putting just hash 4 have the same effect?
Mm, no, it won't, because see, you can't put. Okay, I'll show you what happens. If you put hash 4 over here, you can't do R2 comma hash 4. Okay, this is not valid. Okay, and if you do R0 comma hash 4, it will always offset R0 with 4,
Okay.
R3 with 4. So the only option is to use LSL. I hope that clears it up.
Yeah, got it. Thanks.
Yeah. Does anyone else have any questions? Okay, then I take it you've all understood this question. Just to be clear, okay, just take one more try at that question, the string counting, character counting in a string one. And if you don't understand, feel free to ask on either the Teams group or the WhatsApp chat or wherever, just ask, feel free. But do give it one more shot now that you've seen all this. And that will conclude my session for today. That's experiment 5 for you guys. And yeah, that's the end of the slideshow as well.
Abhishek, we have to give them a feedback form.
Okay,
Yeah,
where
I
do
mean,
I?
no, I just posted the link on the chat. So,
Okay, I see it. Yeah, cool.
yeah. So everyone just make sure, like, just fill out the form. It's just a simple rating, and let us know how much you liked MBSD Lab, like at least our role in it.
Okay, I'll stop the recording. That's fine, right?
Yeah.
That lab question.
Sorry?
The lab 2 question.
Yeah, so if you rewatch the recording, what I did was I explained the bubble sort program, and I asked you guys to take one more shot at it, so that now that I've explained how to properly use the compare instruction, the load store instruction, and how to define arrays and strings, I think you should be able to solve that question. So just take one more try at it. And of course, if you guys don't get it, ask on any of the chat groups, like ask on Teams or ask on the WhatsApp group, and we'll be happy to help you out there.
All
Okay?
right. Thank you.
Yeah. So I'll stop the recording. If there are no more questions, I'll just ask once more. Are there any more questions? Nope. Okay, then I'll stop the recording.